For the case of a single reflective layer that is embedded inside a quiet background, the spectral decomposition response exhibits notching that is periodic as a function of frequency. The period is inversely proportional to the thickness of the layer. This effect is nicely illustrated using a single layer wedge model. But what happens if we look beyond the simple single layer case? What happens to the spectral decomposition response? To investigate this, in 2000 we created a set of wedge models where the gross wedge container geometry remains constant. That is 0 milliseconds on the left and 200 milliseconds on the right. And then filled that gross container with both different numbers of layers and also different thicknesses of layers. In this display, the single layer case is shown at the top. In the matrix below, the wedge models are organized such that the number of layers increases along the vertical axis. The net to gross of the reflective material increases along the horizontal axis. The percent values indicate the ratio of travel time in the white reflective material versus the total travel time in the gross container, where, for example, 50% means that half the amount of travel time inside the gross container is spent inside the white reflective material. If you now look at the spectra for each of these cases, what you find is that different layering and thickness combinations exhibit different spectral signatures. You can then start using such interference information to fingerprint and identify layering scenarios within seismic data. The frequency range for these displays is 0 to 100 Hz. As an aside, there are all sorts of attributes you can calculate from such spectra. For instance, you can consider the number of layers. You find that it takes 8 small amplitude peaks before you hit the main large amplitude peak for a 9-layer case. For a 7-layer case, it takes 6 small amplitude peaks before the main large amplitude peak occurs. So you can start extracting valuable information from these kinds of frequency profiles. The models became more complex with subsequent experiments, but with this first set, we showed the viability of what would become spectral inversion.